All right. Acids, bases, and salt preparations. Let's take a quick review of what we did last time. Last time we talked about salt preparations. Now, before we can prepare any salt, what we are required to do is to know whether the salt is water soluble or insoluble, or probably the third category that is slightly soluble in water. Now, in order to know this, we have this huge table of for the solubility of ionic compounds. We have the key at the bottom, which ones are soluble, which ones are insoluble, which ones are almost insoluble, or very slightly soluble. Now, you aren't supposed to know the reasoning about this, but you are definitely supposed to know about salts so that they can put up you with different salts and different questions and you can answer accordingly. No, memorizing this whole table like this is a bigger problem, so they have actually summarized it into six very simple points, and which makes the whole table and memorizing the table very easy. One, all sodium, potassium, and ammonium salts are soluble. All nitrates are soluble. Most chlorides are soluble except lead, 2, and silver. Most sulfates are soluble except lead, barium, silver, and calcium. All carbonates are insoluble except, again, sodium, potassium, and ammonium. All metal hydroxides are insoluble except, again, sodium, potassium, and ammonium. Calcium hydroxide is an exception, which is slightly soluble in water. So it's really easy. The sodium, potassium, and ammonium, we say up top, are soluble. In the insoluble category, those are the only exceptions. So it's really easy to remember. Moving on, we started it with making soluble salts first. Let's discuss the salts which are soluble and let's discuss how to form them. Now, here comes an exception of sodium, potassium, and ammonium salts. Apart from that any salt that is soluble, we can make it by this category, but this involves the reaction of a solid with an acid. So consider acid reacting with a metal or metal oxide or hydroxide or carbonate. Remember, all of these should be present in solid form with the acid. Don't forget, when it comes to metal plus acid reactions, only the moderately reactive ones from magnesium to iron in the reactivity series can be used. Anything lower than hydrogen won't react. Anything above than magnesium is too violent to react, so we do not perform those experiments in school lab. Be it sodium, calcium, or potassium, they're too reactive, so we're not going to consider them. Which brought us to practical activity number 5. Now, we were supposed to make copper 2 sulfate crystals. As soon as I say the name, it should immediately give you an idea that we need to work with copper, of course, because that's the metal used. But since copper is below hydrogen in the reactivity series, it cannot really directly react with the in acid. In which acid do we need to use? Since it's sulfate salt, so the only acid we'll require in this reaction would be sulfuric acid. Don't forget the parent acid role. Chloride salts are made by hydrochloric acid, sulfate salts are made by sulfuric acid, nitrate salts are made by nitric acid, so on and so forth. So we measure the acid and we heat it on the tripod using the Bunsen burner. We add a spatula full of copper oxide. Remember, the solid should be in excess, the acid should be the limiting reactant, which should completely neutralize and nothing's left out of it, which helps us with the filtration process. Since acid has completely reacted, only the salt is left. So when we're going to filter it, salt will stop on the filter paper and our soluble salt in water would pass. We can evaporate some of the water until we come to a saturation point, which can be checked by dipping a glass rod in the solution. When it's hot, if the glass rod comes out with crystals forming on top of it, stop heating, do not evaporate it to dryness. Let it allow to cool at room temperature. Wash off any of the liquids by filtration or pouring off the remaining solution and dry it by using the paper towel, or you can simply leave it to dry in a warm place. Instead of putting paper towel as your option, since using the paper towel might break the crystals in their structure, it's always wise to write left to dry in a warm place as your answer instead of writing this. This is not a good option. Okay. Now, the question arises here, why do not we evaporate all of the water to dryness? Well, for the most of the salts, there is some water crystallization uh, that comes with the salt, and that actually gives the appearance to the salt. The salt is blue because water is a part of the salt. This water is known as water crystallization. Hence, the salt is known to be hydrated. If we try to evaporate to dryness, the salt will become anhydrous, the formula for which is this, and this salt is known as anhydrous, which means without water. So even the salts have different appearance. Remember, this one has a white appearance, like the table salt we eat every day, and this one is actually blue in color, like you see in the bottom diagram. So that's why we do not evaporate it to dryness, because we then might be evaporating all the water crystallization. Now we can do the same experiment for forming magnesium sulfate crystal, but since magnesium can easily react with sulfuric acid, we don't need any heating. We simply react the metal with the acid. Remember, metal should be more than the acid. All of the acid should react, and then we can get the salt by revising all of the steps afterward. Filtration, evaporation, cooling, then drying, all the same steps in the same way. Remember, those steps can be actually named in the same way. So it's reaction first, filtration after, evaporation third step, drying, cooling fourth step, and drying fifth step. This is the five-step reaction that we can go for. And how would you know whether you need to heat the mixture or not? If you're reacting carbonates or if you're using magnesium as a metal, do not heat the mixture. For most of the substances, if you're taking oxides or hydroxides, or if it's not magnesium, if it's not a carbonate, heat the entire mixture to get your process quick and correct. This is what we studied last time. Let's continue with going with making sodium, potassium, and ammonium salts. And we really need a different method for it. So the first question we have over here, why do we need a different method altogether? Now, your current method is that you add an excess of solid, filter off the unreacted solid, you make sure all the acid is used up, because probably the acid would pass through the filter paper and would interfere with the process. This method does not work for sodium, potassium, and ammonium salts. The problem is that all sodium, potassium, and ammonium compounds are soluble in water. Again, they're going to pass through the filter paper. The solid you added to the acid would not react with acid, but any excess would just dissolve in the water present, and that would easily pass through the filter paper, and you have no way of seeing it with the naked eye, so you won't know how much to add just to neutralize the acid. So we can't really take that risk and allow these salts to pass through the filter paper and every time become a part of the crystal with it. So the method we have given previously will not work with sodium, potassium, and ammonium salt and will totally fail. We definitely need a new method. So how do we do it? We solve the problem by doing a titration. Now you already know how to perform a titration. You know how to take the acid or the alkali, how to ready up your pipettes or burettes, take the solutions, use indicators, and finally get uh, your titration complete. But will you be able to take the salt out of it then? Actually, you can, but you might need to perform the titration the second time and without the indicator as mentioned in these lines over here. So let's go through over the whole process and make sure that we carefully cater those steps to our own advantage. The start of the titration might seem the same, but the last steps of the process will be a little bit different so that we can focus on the salt we require. Let's suppose the salt we require is sodium sulfate. As soon as you see the name, I hope you understand you need to use sulfuric acid, as this is a sulfate salt. As soon as you see sodium, I hope you understand you cannot really use the metal sodium since the reaction is going to be too violent. So either you need sodium oxide or you need sodium hydroxide. which we have used in previous titrations, by the way, or you need sodium carbonate. Now you can really use any one of those. All of them are soluble, but we'll use one of them in the process. Let's see what we use. So 25 cubic centimeter of sodium hydroxide, I think that pretty much clarifies it, is transferred to the flask using a pipette. Add a few drops of methyl orange indicator. Remember, this indicator is orange in neutral solution. It becomes yellow in alkaline, and this yellow will be converted back to orange once we use the acid and neutralize it. Remember, if you use a single drop more, this orange will be converted to red because it is red in acidic solutions. So if you're performing that experiment and you accidentally convert your yellow to red instead of orange, you should instantly know that you have used more acid than required. You might need to dispose of the entire solution and do the titration again. Because orange is the endpoint color you need, not red. So, moving on, the volume of acid needed is noted. And what we do after that is that we take same volumes of acid and alkali and we simply mix them in a clean flask without any indicator. Now we know how much of alkali and how much of acid are actually required for the neutralization process. So this reaction would simply occur, will form our sodium sulfate salt along with water. Now go off with the rest of the process. Evaporate some of the water, form a saturated solution, allow it to cool until transcrystals form, separate those crystals, and then let them dry by leaving them in a warm place. Your process is complete. Again, this is also salt which has water crystallization present in it. So if you're going to evaporate it to dryness, you might end up with an anhydrous salt, which is not really what you require. Now remember, the key point is mentioned over here. Methyl orange is red in acidic, yellow in alkaline, and orange in neutral solutions. So from yellow to orange is what you need to obtain. Orange is a mixture of red and yellow, so sometimes it's a little bit difficult to differentiate between the colors. But once you perform this entire experiment with your own hand, you will easily be able to do it next time. Okay?
Mhm.
Little bit of extension work. Methyl orange actually changes color between these pHs, and below these pHs, methyl orange is red because it's acidic. Above, it's yellow because methyl orange really changes color, and not exactly at neutral, but in between these points. Between these pHs, methyl orange will be a mixture of red and yellow. That is orange, which means it's actually yellow with solution with pH 7. This technique does not therefore give us the exact neutralization point because the pH really rapidly changes at the end point of the titration. Even a single drop can bring a huge pH difference. So neutralization point to the nearest drop of acid is very good. The more careful you are about the experiment, the better endpoint color you're going to get. If you're a little bit careless, as I've told you before, and this extension work tells you the same, you might end up in having red rather than orange, which is not correct. Again, we can perform this experiment to get sodium chloride salt, the table salt we eat every day. By the chloride word, I hope you understand we need to use hydrochloric acid. Again, for sodium, sodium hydroxide is a great source. This is how you would go for the titration. Remember, once you have premixed the acid and alkali without the indicator, evaporate the solution to dryness rather than crystallizing it slowly because sodium chloride crystals do not contain any water of crystallization. So if you know a salt that does not contain any water of crystallization, it's really easy for you. You can completely evaporate the water. But there is a disadvantage. There is a downside. If you do that, you would either get a powder or very tiny crystals. So if you need bigger crystals, you're not supposed to evaporate to dryness. Whichever kind of salt is that, whether it has water of crystallization or it hasn't. Okay, so we prefer not to evaporate to dryness. Always try to go for the saturation point, check for saturation, turn off the heat, and allow the solution to cool at room temperature. And then afterwards, it's cooled down, it has settled. Then you can take out the crystals, separate them, and allow them to dry in a warm place. That's the best solution that you can go for. Making ammonium sulfate crystals, as the name suggests, sulfate means you're about to use sulfuric acid, ammonia means you're about to use ammonia solution. So again, you can go for this. Now, using ammonia solution rather than sodium hydroxide does not bring a difference to this method. Although simple ammonium salts do not have water crystallization, you would still crystallize them slowly rather than evaporating them to dryness. Heating dry ammonium salts tends to break them up, so you shouldn't heat them too much. Keep this point in mind about ammonium salts so that you do not heat them too much in exams. This is specifically noticed in Edexcel. So remember this line, which finishes for us the preparation of all kinds of soluble salts, be it sodium or ammonium or potassium salt, or be it simple soluble salt, which leaves us only with one portion, making insoluble salts. All right, so let's
Mhm.
go with this one. In order to make insoluble salts, the process is known as precipitation. And insoluble salts themselves are known as precipitates. And we call these precipitates as an abbreviated word of PPT, which stands for precipitate, insoluble salt. Now, as the word insoluble suggests, they are not soluble in water. Of course, these salts are going to settle down at the bottom of whatever utensil or test tube or beaker or flask you're going to use. Let's come towards the preparation. The basic procedure is to mix solutions of two soluble salts, and they are going to give us two products, one insoluble salt and one soluble salt. For example, and we're going to try making some insoluble salts, but before we do, I'm going to take you a little bit back to the same table. Now, which salts are insoluble and you can make them? This you can know from the table and always know these are the salts which you might be preparing. These kind of salts. These salts are the insoluble salts which you might be preparing any of these, right? So whenever I am about to take an example, preparing an insoluble salt, it would be something out of here. And as you can see, the first example was of silver chloride. Now, why did I exactly pick or the book's author exactly pick up silver chloride? Because it's an insoluble salt. Remember, in this entire topic, we'll only be catering these examples, any one of these, right? So keep that in mind. That's a simple common sense point that one should know. So getting back to insoluble salts, so we are supposed to prepare this insoluble salt. For this, we have written solid, not aqueous. Why? This does not dissolve in water, so you can't really write aqueous as a state symbol next to it. That would be wrong. As we have just said that you dissolve two soluble solutions, you get one insoluble and one soluble solution. So the equation for precipitation would mostly look like this. Aqueous plus aqueous gives you solid plus aqueous. This is a precipitation reaction. Precipitate is that exact solid which is formed by the chemical reaction. This may also involve liquids or gases. Precipitation reaction simply produces a precipitate or a solid that is insoluble, so it settles down and does not dissolve. Sometimes the precipitates have colors, like it can be white, it can be yellow, it can have different colors. Since they don't dissolve in water, you can easily separate them with the method of filtration. Now notice what we have combined together. Coming back to the equation, notice we have silver nitrate and we have sodium chloride. Now these reactions are pretty simple and you can really divide them into positive and negative ions part. The positive part of first salt combined with the negative part of the second. This gave us our insoluble salt. Vice versa, the positive part of the second salt combined with the negative part of the first. This gave us the soluble salt. So it's always going to occur like that. Precipitations are really easy. The first half of the first salt combines with the second half of the second salt, or vice versa. The first half of the second salt combines with the second half of the first salt, and that's how we're going to get one insoluble and one soluble salt. It would happen every time the same. Let's explain what's happening over here in a very detailed diagram. What just happened was that our silver ions and nitrate ions, when they combine together from two aqueous solutions, they actually form, uh, silver ions and nitrate ions are dissolved in water in an aqueous solution. Chloride ions and sodium ions are dissolved in aqueous solution. What happens is that sodium and nitrate ions are spectator ions. They really dissolve and they move around the whole solution. But silver and chloride ions stick together, they form a solid, and that solid tends to settle down. Notice the structure of solids look like a solid, and the structure of aqueous solution looks like a roaming small ions around the solution. The water molecules in the solution have been left out to avoid cluttering in the diagram so that the diagram does not confuse you. But remember, there is water all around the system, or this one for that matter. Now let's go with the exact explanation given over here. Silver nitrate solution contains silver ions and nitrate ions. These are positive and negative ions attracted to one another, but attractions are strong enough to them to stick together. Similarly, sodium chloride solution contains sodium ions and chloride ions. Again, the attraction are not strong enough. But when we mix them together, the various ions meet each other. Now, silver ions meet chloride ions. The attractions are so strong that the ions clump together and form a solid. They don't really bother while forming a solid that whether they would be soluble or not. They just try to stick together because they have strong forces of attraction. All right. So the sodium and the nitrate ions, they remain in the solution. They aren't sufficiently attracted to one another. Plus, water tends to dissolve them too, since they're very much soluble. So that's how we get the precipitates of silver chloride. This is a very good explanation of how a precipitate forms, which really brings us to our extension work. How would you write the ionic equation for precipitation reaction? Now that's really easy. You only need to require the ions of your insoluble salt and you combine them for a precipitation reaction. So take your positive ion for the insoluble salt, take your negative ion for the insoluble salt, both in aqueous form, reacts to form the solid or precipitate. That's how easy it is to write the equation. Remember, do not forget to write the state symbols. It's aqueous and aqueous on your left, it's solid on your right. And every time it's going to be the same. Let's consider another example. Barium sulfate is another insoluble salt. It is made up of barium ions and sulfate ions. Write both of those ions with aqueous on your left and write the salt as solid on your right. There you go. You have your ionic equation. That's how simple it is. For example, let's think of something else. Calcium sulfate is insoluble. So how would you write the equation? Write calcium, aqueous, sulfate, aqueous. Now, since we know these both of these are ions and sulfate has a negative 2 charge, that must mean calcium belonging to group 2 has a positive 2 charge. So we mentioned their states, write it like this. And finally, just a second. And finally, you can write your calcium sulfate salt with the solid sign. There you go. You have the ionic equation. So even if you just know the name of your salt or the formula of your salt, writing the ionic equation for precipitation reactions is really easy. It really does not matter which two salts we combine to get these. They really don't matter. We might have combined calcium nitrate with, let's say, sodium sulfate to get these, but really does not matter. My bad, sodium sulfate. All right. Now, this comes as a question from students. Students ask, how would we know which two salts to combine? Now, don't worry, your book has all covered up. Now, what do we mix together to form our insoluble salt? The million dollar question. So, since all nitrates are soluble, so let's say if you're supposed to form this salt and the negative ion is sulfate and the positive ion is this, since all nitrates are soluble, make sure for this positive ion you take its nitrate salt. So always go for calcium nitrate. If you're supposed to form this silver chloride, you know this is your positive ion, this is your negative ion. So try to take its nitrate salt. My bad, we shouldn't be using the bracket sign. So try to take its nitrate salt. This is the first point of this topic. For your negative ions, always try to take their sodium or potassium salts because those are soluble. So either you can take sodium sulfate or you can take potassium sulfate. Again, in this case, either you can take sodium chloride or you can take potassium chloride. Now mix this one and this one up, you'll get silver chloride, or mix this one and this one up, you'll get silver chloride. Again, it's in the case of calcium sulfate, mix calcium nitrate or sodium sulfate, or calcium nitrate and potassium sulfate, you'll get calcium sulfate. That's how we do it. That's how easy it is. So let's say he gives you something out of the ordinary. Now, potassium iodide, which is given as an example over here, does not exist in the table above. Let me take you to the table. Let me clarify this. Lead iodide. Remember the name of the compound. I'm going to take you back to the table. Now, notice this table does not even have iodide. This table does have lead. You can see the lead over here. This table might have nitrates or chlorides or sulfates or carbonates or hydroxides, but this table does not have lead iodide. Now, book is asking about something out of the ordinary. Do not get confused with it. Again, lead is the positive ion, iodide is the negative ion. So for the positive ion, try to take its nitrate salt. And for the negative ion, try to take either the sodium salt or the potassium salt. There you go. Mix these two. You can easily form lead iodide. And you see the exact same thing done by the book. Let me take you right there. Is it the exact same thing or am I mistaken? Let's check it out. Yes, that's the exact same thing. They mix lead nitrate and potassium iodide. There you go. You form lead iodide, which is our precipitate, the beautiful yellow colored precipitate you can see on your left, and it also forms an aqueous salt, which really does not matter because they are spectral. How do you write the equation? Even for something unknown, if you have the name or the formula, you can come up with the equation. Again, let's take another example, which I probably have already clarified, barium sulfate. Now you need a salt for barium, try going for nitrate. Need a sulfate salt, try going for potassium or sodium sulfate. There you go. You have your answer. Barium sulfate is a white precipitate. And this is the ideal equation, which I've already covered. Let's cover this as a part of practical. So your activity, preparing a pure dry sample of an insoluble salt. In this case, we have lead sulfate. To take the lead nitrate again, and it's the same quantity of sodium sulfate. Amounts really do not matter because we're going to get rid of excess later. A white precipitate of lead to sulfate will form. This is your equation. Filter out the reaction mixture. A white residue of lead to sulfate is left on the filter paper. There is a colorless solution of sodium nitrate and any excess reactant. They have already passed through the filter paper. You can wash the residue a couple of times with distilled water if you want to, which is our very next step. Wash the residue with distilled water by pouring 20 cubic centimeter portion. Portion is not important. but allow it to filter through the past paper. This washes away everything apart from insoluble lead to sulfate. This process should be repeated several times. So wash with distilled water like 3 times, 4 times, or 5 times, several times. Make sure that your sample is washed from every single side. There is no dry part or there is no contamination left. We then transfer the filter paper and the lead to sulfate on top of it to warm oven or any warm place to dry. The water would evaporate. There you go. You have the pure dry crystals of your precipitate with you. Remember, you always wash with distilled water or pure water, never tap water, because tap water has impurities, and those impurities are going to mess up your whole process, your whole practical. They will easily contaminate your salt. Which brings us to the summary of your method. You really use three methods. The first thing you need to ask yourself before you pick a method is that, is the salt soluble? If the answer is no, use the precipitation technique because we use this technique for all insoluble salts. If the salt is soluble, think about the salt. Is it a sodium, potassium, or ammonium salt? If it's not, you need to take excess of the solid, react it with a little amount of acid, and form your salt. Of course, the next steps would be filtration, then cooling, then evaporation, then cooling, and then drying. My bad. And if it's exactly a sodium, potassium, and ammonium salt, use the titration technique. First, titrate it with indicator. Secondly, titrate it without indicator. The rest of the process part go accordingly. You then evaporate it. You then cool it, dry it. There you go. You're done. So this clarifies our topic for today. We have a little bit of theories of acids and alkalis to go for. These are hardly a few pages, I guess 2 to 3 pages hardly. So this we're going to do in next sitting. I guess this is good enough for today. Do you think the same?